Hello, everybody. I hope you're all doing well. So, we're going to be looking at the idea of an instantaneous center of rotation today, and this is a concept that is used to perform velocity analysis of rigid bodies. Okay, so let me write that down. Instantaneous center, that's a pretty long word there. So, instantaneous center of rotation. Okay, or this is called as ICR. Okay, this is used for velocity analysis of rigid bodies. Okay, and so I just want to underline that this is used for velocity analysis, which means that do not use this same concept for acceleration analysis. It does not tell us anything about the acceleration of a point on the body. Okay, my familiar problems of drawing straight lines. All right, so it's used for velocity analysis only. Do not use this for acceleration analysis. That's going to be done by using your regular vector method. Write the equations and then try to find the velocities using the equations. Okay, this is just a shortcut for certain types of problems. It is much more of a use when you go to study kinematics of mechanisms and so on later. So this is a good reason to introduce these concepts to you. Okay, and this is also useful in gear kinematics and so on. Okay, the instantaneous center of rotation. All right, so what exactly is this? So to understand this, I'm going to revisit my problem of rolling without slip. Okay, so to understand ICR, I'm going to revisit the concept of roll without slip. Okay, and let me do this by taking a very simple and silly example. Okay, I'm just taking a disk, and this disk is rolling on a flat surface. Okay, so let's say that this is the flat surface. Let me draw a straight line, and then all right, fantastic. And let's say that this surface is a fixed flat surface. Okay, so this is a fixed surface. Okay, and I'm assuming that the disk is rolling in the clockwise direction. Okay, so it's rolling forward. So I'm going to say that, okay, this is omega of the disk. Okay, and let's say that here is the center of the disk, which is called as the point O here for me, and then let's say that here is a contact point between the disk and the ground, and here is the fixed surface itself, which I'm going to call as G. Okay, or let me call it as B. Okay, so this is point C, and then this is point B. I'm going to have a vector this way. I'm going to make use of this vector very soon, so I'm just going to draw it anyways preemptively. Okay, and let's say that the radius of the disk is capital R. Okay, so this is some capital R. Okay, so since it is a fixed surface, and then I'm also saying that it is rolling without slip, so this is also roll without slip. I know that the velocity of point C relative to point B has to be 0. Okay, so roll without slip implies that the velocity of C slash B has to be 0, which implies that velocity of C is equal to velocity of B as seen by an absolute or an inertial observer or from an absolute perspective, but the ground itself is fixed. Surface is fixed, which means that velocity of B is 0, which implies that velocity of C, which was the same as the velocity of B, is now 0. Okay, I hope this makes sense. This is at that instant in time, of course. At that instant in time. So at that particular instant in time, C is a contact point with respect to the ground. So let me maybe clarify this. So at that instant in time, at some time instant, the disk contacts the ground at point C on the disk. Okay, this is at that instant in time. Okay, this is instantaneous, which is why you have the term instantaneous coming into the heading of this talk itself. Okay, so what this means is that at that instant in time, since the velocity of c is 0, it is as if the entire disk is trying to rotate about the point C. Okay, so let me write this down. So since the velocity of c is 0 at that instant, this implies that it is as if the entire disk is trying to rotate about this point C at that time instant. Right? Because if imagine you have a pendulum, right? The pendulum is fixed to a pivot, and the pendulum is trying to rotate about that pivot point. So obviously, at any given instant in time, the pivot is going to have a zero velocity. Such a point is a fixed point. What I'm saying is that at that particular instant in time, this point C is behaving as if it's a fixed point. At the next instant in time, the point C has lost contact and then it will have a velocity. Okay, so at that instant in time, the point C behaves as if it is the center of rotation. Rotation of the disk, okay, because it has zero velocity, and such a point is called as an instantaneous center of rotation. Okay, so such a point is called the instantaneous center of rotation. Okay, this is only at that particular instant in time. The next instant in time, the point Z has lost contact and it will now have a velocity. Okay, this is something that you want to note. At the next time instant, point C would have peeled off from the ground and will have some velocity. As a different point comes in contact with the ground, as a different point on the disk comes in contact with the ground. Well, I'm trying to write it down there so it doesn't let me do it. I'm going to sneak it up here and then write the D. All right. So that is something that you really want to make a note of. Okay, so this is only at that particular instant in time. I cannot stress this enough number of times, because if the point C becomes a point which is at zero velocity forever, then that's a fixed point. Okay. Now note that this does not tell me anything about the acceleration of C. Okay, so the fact that, one more note, okay, this is with a red color here so that you know this is a danger note. Okay, the fact that C is the ICR does not inform me of the acceleration of C. The only thing I know about the acceleration of C is it's rolling without slip, so its tangential acceleration is going to be the same as the surface. But that's not a consequence of C being the ICR. That's a consequence of rolling without slip. Okay, so that's what I want to make a firm note of. Okay, and so this is the nice thing. Once again, I just want to very briefly go back and then look at it. We are not done, of course. We are going to be elaborating on some more aspects of this. But the instantaneous center of rotation is any point on the rigid body that has a zero velocity at that instant in time. Okay, so that's called the ICR. So let me very succinctly write that down. So define the ICR. Okay, so this could actually be a point on or outside the rigid body. So any point on or outside the rigid body that has a zero velocity at that time instant. Okay, once again, this does not inform me of the acceleration of the point or anything of that matter. Okay, so please keep that in mind. So ICR can be either on or outside the rigid body, so note that too. We are going to see situations where I can have an ICR outside the rigid body. Once again, the straight line business is kind of butchering me here. All right, now the other note is if the ICR at one instant is also the ICR at the next instant, then such a point is nothing but a fixed point. Okay, so if by chance the ICR at one instant is also the ICR at the next instant, then this is nothing but a fixed point. Such a point is nothing but a fixed point. This is similar to the fixed pivot of a pendulum. Okay, all right. And then, so what happens is the following. Okay, let me go back to my disk once again. Okay, let me bring in all of these creatures. Okay, I'm going to copy that and I'm going to bring that down here. Okay, now I know that the velocity of C is 0 because C is the ICR. So C is the ICR, which means that velocity of C is 0. Then I can say, okay, point O and C on the same body, which means that velocity of O slash C relative is 0 because the distance between them is fixed. And so I can say that velocity of O is velocity of C, O slash C relative, omega disk cross R, O slash C. I can cancel off this term, I can cancel off that term. Okay, which essentially tells me that velocity of O is going to be omega of the disk crossed with R, O slash C. If I assume that the disk is rolling clockwise, okay, then I'm going to set up a coordinate frame here very quickly. So this is I, J, and K for me, as you know. This is J, this is I, and this is K. Okay, and I can write this in the form of a triad I, J, and then K, as I'm doing my cross products and so on. Okay, so here is my triad, which I can come and then write on top of the disk here. And then if I do the following, velocity of O is now omega of the disk, which is minus omega disk in the K. Let us say that this is rolling clockwise, as you can see from the arrow, crossed with the position vector from R, O to C. Right, this is going to be R, O slash C. So this is going to be some radius R, or capital R, in the J direction. K cross J is minus I from the triad, which means minus minus becomes a plus. So V naught is going to be R times omega D in the I direction, or this is the direction of the velocity of point O. Okay, And this is important. Why is this important? I'm just going to redraw this one more time, okay, for the following reason. Okay, so now I know that if I have the point O here, okay, if that is my point O, and then if this is my point C, which is contacting the surface, it is almost as if I can do the following. Okay, I can almost do the following. I can say that this point C is like a fixed point. This is the ICR. Okay, so this is the point C, and then this is the point O, and then I can see that if I draw a line joining point C and point O, the angular velocity of the disk, if I assumed it to be clockwise, okay, if this was omega of the disk, and then I see that the velocity of point O is going to be perpendicular to the line joining the point O and the point C. This is going to be velocity of point O, which means if I choose a different point, if I choose a different point here, okay, if I call that as point A, and then if I join the point A and the point C, then I know that the velocity of point A has to be perpendicular to that line. And if I use the following, okay, look at this. Maybe let me write this down. So I know first of all that the velocity of O is perpendicular to the line joining O and C, and I can actually find out the direction of the angular velocity if I know the velocity of O. So if we knew velocity of O and if C was the ICR, we can find direction of omega. Okay, just by making use of the right hand rule. Okay, align the fingers with the velocity direction V0. Your palm faces the ICR. You curl your fingers and it's clockwise. Okay, so here is what you do. Align right hand along V0. Palm faces the ICR. Curl your fingers. That tells you that the sense and the direction of the thumb will give you the direction of the angular velocity. Okay, so if I do these things, then I am able to get the direction of the angular velocity. Okay, so this tells me that if I do this on our particular problem, so if I do the combination of all of these things, tells us the direction of omega of the disk, okay, which essentially tells me, okay, if I do the same thing at the point A, then I know that the velocity of A has to be pointing this way. Okay, so this has to be the velocity of A, that's perpendicular there. If I choose a different point, if I call that point as a point D or something, whatever it is, I can then join these two lines from the ICR, and then I can say, hey, this is going to be the velocity of D, which is going to be perpendicular to the line joining the two, and then based on the right hand rule, I know that the velocity has to be pointing this way, because only then can I get a clockwise rotation of the rigid body. Okay, so this is really powerful, right? If I know something about the ICR. So maybe I want to summarize all of these findings. Okay, so let's make a summary or a list of all of these findings and why the ICR is useful. Okay, so why finding the ICR is useful. So summary and usefulness of the ICR. Okay, so that's something that I want to mention here. So first point is the following. Okay, at any instant in time, at that instant in time, ICR is a point on or outside the body. Okay, about which the body tries to rotate. which implies that the velocity of the ICR is going to be 0. Okay, so this is the first point. This is what we've been talking about at that instant in time. Okay, so this is at that instant in time. Okay, the second thing is that the ICR is always along, let's see here, ICR always lies along the line that is perpendicular to the velocity of any point in the rigid body. That is perpendicular to the velocity of any point on the body. And case in point is this disc here. I'm going to just bring this disc in and keep it right out there. Okay, so this is the situation. You see, the point C is the ICR, right? This point is along the line that is perpendicular to the velocity of A. This point is along the line that is perpendicular to the velocity of O. It's along the line that is perpendicular to the velocity of D, and so on and so forth. Okay, so this is something that you can automatically see here. Okay, then the third thing I can say. So the important thing is this always lies. This is a key statement. Okay, this is a key finding of what we have done so far. It always lies along a line that is perpendicular to the velocity of any point on the body. Not just a single point, but any point on the body. Okay, and then the third point that I want to make, which is an equally important point and which we just spoke about in terms of the right hand rule and so on, is the following. Okay, so let's say that if velocity of P is a point on the body, okay, let me just take an arbitrary body here. Okay, so let's just say I have some point P, and here is the velocity of that point. Okay, so say Vp is the velocity of some point on an arbitrary body. Okay, and let us say that omega is the angular velocity of the body. Okay, let's say this omega, let's say, is the angular velocity of the body. So say omega is the angular velocity of the body. Let's say that at some point in time this is the instantaneous center. Okay, so first of all, here is what I would do. Before I draw the instantaneous center, I would draw a line that is perpendicular to this velocity here. Okay, what we know is that the instantaneous center lies along that perpendicular line. Let us assume that this point is the instantaneous center at that instant in time. Okay, so let us say that this point C, so say C is the ICR at that instant, and you can also see that this point ICR is on line that is perpendicular to the velocity of P, as you can very well see here. Okay, so if I know the location of P, if we know location of C, and if we know velocity of point P, which means that if I know this distance, let's call this distance as R, P slash C. If I know the distance, then I can find the angular velocity of the body. Then angular velocity of the body, omega, can be found out. How do we do this? Here is how we do it. I'm taking this figure once again. I'm going to copy that, and I'm going to bring that down here, the magnitude of omega. How do I find the magnitude of omega? I can see easily that velocity of p is going to be rp times omega, which means that omega is going to be velocity of p divided by rp/c, because point C is a fixed point at that instant in time. It's not fixed as such. Its acceleration is not necessarily zero. It does not tell you anything about the acceleration of the instantaneous center of rotation. Okay, please keep that in mind. But I can find the magnitude of the angular velocity this way. And then I can also find the direction. Direction of omega, I have to use the right hand rule. Okay, here is the right hand rule. Okay, align right hand along the direction of VP. Okay, just follow along with me. Then you face your palm towards the ICR. Then curl your fingers. The curl of the fingers tells you the sense of the moment, sense of the rotation. Will give you the sense of omega, and then the thumb gives you the direction of omega. Okay, and if I follow that particular idea here, I will see that my thumb is pointing into the page, which means that for me here omega is going to be this way. So this is omega of the body, which is going to be pointing this way. Okay, so this is extremely important. Okay, so this essentially tells us that if I know the location of the ICR, so which tells me if we can locate ICR, and if we know the velocity at any point, velocity of any point on the body, we can then find the angular velocity of the body. Okay, so this is something that is important. Okay, so this was I think point number 3, and the last point that I want to make before I go and look at some cases. Okay, I will not take up too much more of your time, but I do want to get through with this. The last point is knowing the ICR does not tell us anything on the acceleration of the body or the point. Okay, so ICR is used only for velocity analysis. Okay, so which tells me that ICR is used only for velocity analysis. Okay, so this is something that you want to really keep in mind. Okay, so ICR is used only for velocity analysis. All right, so what am I going to do now? I'm going to look at several cases, okay, which is essentially I'm going to take a rigid body and then say, okay, how do I find the information regarding the rigid body if I'm given some other information? Okay, so how to find the ICR? Let's do this case by case. Okay, so how to find? Let me not write it this way. So how to find the ICR? Okay, let me look at different cases. So case 1. So I'm now given two non-collinear and two non-parallel velocity vectors on a rigid body at that instant in time. Okay, so given two non-collinear collinear and non-parallel velocity vectors on the body at that time instant. Locate the ICR. Okay, so let's say I have this following rigid body, okay, some arbitrary potato here, and I'm saying, okay, hey, here is a point A, and I'm saying that, okay, the velocity of this point is given to me. Okay, so velocity of A is known to me. Then I'm saying, okay, hey, let me say there is another point on this body that I have. This is point B, and the velocity of this point is given to me. Okay, so the velocity of this point is given to me this way. Okay, I need to find the ICR. Okay, so this is velocity of B. So given VA and VB, locate the ICR. How do I do this? First thing I do is this. Okay, hey, I know that ICR is going to be along a line perpendicular to the velocities. Okay, so I'm going to draw a line that is perpendicular to the velocity of point B. Okay, so this is a line that is perpendicular to the velocity of point B. Then I also know that the ICR is going to be along a line that is perpendicular to the velocity of point A, which means I'm going to draw a line that is perpendicular to the velocity of point A. Okay, that was not necessarily straight. Let me draw a much straighter line and let me adjust it. Okay, so this is a line that is perpendicular to the velocity of point A. So here is a line perpendicular to A, here is a line perpendicular to B, where ICR has to be along the line perpendicular to both the velocities, which means obviously that this point here, which is the point of intersection, is going to be the ICR. And you see that it is not necessary that the ICR be on the body. So this is going to be the ICR. Okay, this is the location of the ICR. And if I now know the distance from point A to the ICR and point B to the ICR, okay, so if I know this distance here, okay, so if I call that distance as some R A to ICR, if I know that distance, then if we now know RA ICR, then I can say that VA is omega of the body times RA ICR, which means that omega is VA by RA ICR. This is the magnitude. How do I find the direction? The direction can be found by using the right hand rule. Take the fingers of your right hand, align it to the velocity VA, your palm faces the ICR, curl your fingers into the page, which means that the angular velocity of the body is going to be pointing this way. Okay, so once again, how did I find this ICR? I draw a line perpendicular to the velocity of B. I draw a line perpendicular to the velocity of A. The point where they have to intersect is where the ICR is. Okay, so to locate the ICR, draw a line perpendicular to VA, draw a line perpendicular to VB, wherever they intersect. Wherever they intersect, this is going to be my ICR. So simple and so elegant, right? Now if I know the ICR, then I can find the angular velocity of the body by using all of these things. Okay, so this is exactly the use of finding the ICR. Let's look at the next case. Okay, so I'm going to look at case 2. So in case 2, let us slightly tweak it up. Okay, let us consider, let's say that we are given two non-collinear But parallel velocity vectors locate the ICR. Okay, so how do I do this case? And this did not seem like a straight line, but yeah, now it is straight. All right. So let's say that I have a point here. Okay, let's call this as point A. And let's say that here is another point which I'm going to call as point B. Okay, so I'm given the velocities at A and velocity at B. So I'm given this velocity here. Let me scoot this up and draw it out a little there. So this is the point A. I'm given the velocity of this particular point. Okay, so this is VA, and I'm given the velocity of point VB. How do I find the ICR? Exactly the same idea. Okay, draw a line perpendicular to VA. So let's draw that line. Okay, so here is a line that is perpendicular to VA. Then what do? I draw a line perpendicular to VB, and then wherever they intersect, is going to be my ICR. But I am in for some troubling times, because I see that if I'm drawing a line parallel to VA and then parallel to VB, I see that these two lines are parallel to each other. They never intersect, or they intersect at infinity, which means that the parallel lines intersect at infinity, which means that the ICR of this body is infinitely far away from the location of point A and the location of point B, which means that the ICR is located at infinity. That's very weird, right? Which essentially tells me that the position from the point A to the ICR is infinite, and the distance from point B to the ICR is also infinite. Okay, so infinitely large, or very large. Okay, so what is the ramification of this is the following. We also know, though, velocity of A has to be omega of the body multiplied by RICR. Velocity of A is a finite quantity, which means that omega of the body is velocity of A divided by RA ICR, which in this case is approximately 0, because RA to ICR is approximately infinite. So which essentially tells me that this rigid body is in pure translation. Omega of the body is 0, which tells me that the body is in translation at that point in time. Okay, or probably its velocity is going to be changing at that point in time. Angular velocity is changing at that point in time. Okay, so this essentially tells me that the velocity of A is the same as the velocity of B. Okay, because omega is very small, r is very large, which essentially tells me that velocity of A is equal to velocity of B. So that's the second case. Okay, interesting case. I have velocities given. How do I find ICR? Draw lines perpendicular to the velocities. I draw these two lines, and then I eventually see that, okay, hey, if this is the situation, then they never meet, because they meet at infinity, and so there is no ICR here. Or if there is an ICR, it's located at infinity and it's infinitely long. And if I calculate the angular velocity of the body, it's going to be 0. Okay, then I go to case 3, and we're almost done. Okay, so that was case 2. I want to see if I use Roman numerals or so. Oh no, I use the usual cardinal numbers here, 1, 2, and 3. All right, so given two parallel non-collinear velocities, okay, as shown in the following situation. Okay, obtain in this case these are like collinear. I'm sorry about that. In this case they are along the same line. Well, if I join them together, they're on the same line. So I guess the velocities themselves are non-collinear. They're not coincidental, I'm sorry. So they are non-collinear. Obtain the location of the ICR. Okay, so what am I going to do in this particular case? Okay, let's see. So here, let's say that, and these two velocities are along the same line. I mean, the 2 points are along the same line. So, and the important difference between the previous case and this case is that the points that I'm given the velocities are on the same line if I join them together. Okay, so which I'm going to show in a second here. So let's say that this is point A. Okay, and then this is point B. Okay, they're lying one below the other. This is one velocity. Let's say that this is another velocity. So this is velocity of A, velocity of B. Okay, if I join the 2 points A and B, then they're lying one below the other. So A and B are coincident. Okay, how do I find the instantaneous center? Draw a line perpendicular to VA, draw a line perpendicular to VB. Okay, point of intersection at the ICR. Now this is going to be interesting. Okay, I'm drawing a line perpendicular to VA, I'm drawing a line perpendicular to VB. It looks like they're the same straight line. Okay, then how do I find the ICR? So we know that the ICR is going to be along this line. Okay, so we know ICR is along the blue line, right? We also know that the velocity at the ICR is 0, right? Which means that if I know that velocity of A is greater than the velocity of B, okay, so if we know VA, the magnitude is greater than the magnitude of VB, let's say if this is the situation, then, and we also further know that VA is R A slash ICR to omega, VB is R B slash ICR to omega. What does this tell you? This tells us that the velocity linearly increases with distance. Okay, velocity linearly increases with distance from the ICR. So which means that here is what I have to do. All I have to do is take a line and then join the head of these velocities and then extend them here, which means that wherever that is going to intersect this line is going to be where the ICR is located. I hope this makes sense, because this automatically tells me that, okay, hey, the velocity of A is some r times, okay, let's draw the distances. Okay, let's do that here. So this is from point A all the way to the ICR is one distance that I have. That's not straight. I'll try to make it straight. All right, fantastic. So this is R A slash ICR. I want to make some space to write that out. Sorry. This is R A slash ICR, and then I also have RB slash ICR, which is this distance here. So this is R B slash ICR. If I'm at a shorter distance away from the ICR, the velocity is smaller and it's linear, as I can see from these two equations that I have written here, which means that the velocities have to be along the line joining the intersection and the tip of their arrows joined together. Okay, so that's going to be the ICR for me. And if this is indeed the case, then I know what the angular velocity is going to be. Angular velocity is going to be VA divided by RA ICR. If I use the right hand rule, I can automatically figure out that the angular velocity has to be this way. Okay, and so this is one situation. Okay, and another situation is I could have another case, the same thing, but I could have a different case where, let's say, I have this point here and then this point here, same as before. These points are along the same straight line. Let's say that here is the velocity of A pointing this way. They're not in the same direction. Let's assume that they are in different directions. Okay, this is the velocity of B. This is the point A. This is the velocity of A. Okay, how do I find the ICR? Once again, the same idea. Okay, I draw a line perpendicular to the two velocities. I could actually probably bring this picture down up here so that I can save this for the last case. Okay, let me bring this situation here. Okay, so this is another case. So this is the line that is perpendicular to the velocities of the 2 points. I know that the velocity at the ICR has to be 0. I'm seeing that the velocity is changing directions here because the velocity at the ICR is 0. Then I realize that, okay, hey, the ICR actually has to be in between these 2 points, which means that this guy is now going to be the ICR. Okay, which means that this distance here is going to be RA slash ICR. That distance is going to be RB slash ICR. And if I want to find the angular velocity of the body, right hand rule, align fingers with the velocity VB, your palm faces the ICR, you curl your fingers, you will find out that the angular velocity in this case is going to be pointing this way. Okay, so it is either this situation or the previous situation here. Okay, where the velocities were in the same direction but they were not equal in length or equal in magnitude. Here also they are not necessarily equal in magnitude, but they are pointing in opposite directions. So I can also have this situation here. Okay, so once again, these are two important cases. They are of the same category. As you can see, the velocities are parallel to each other. The points lie along the same line and along the line that is perpendicular to the direction of the velocities. Same case here, the points lie in a direction on a line that is perpendicular to the two velocities, and the velocities are parallel but they are in opposite directions. Okay, this is different from the previous case where I had the velocities parallel in this situation as well, but then the points A and B were not coincident. Okay, they were not lying on the same line as if I drew a line perpendicular to the velocities of A and B. That was not the case. So in that situation, the angular velocity of the body was approximately 0. In this case, that is not so much the situation here. Okay, and lastly, we can also say the following. Okay, given, okay, so let's just call this as case 4. This is not necessarily a case as such, but something that could be of use to us. Okay, so given the last one, omega, given ICR, we can find the velocity of any point on the body. Excuse me. Let's say this is the situation. Okay, I have a rigid body, omega of the body is given to me. Okay, and then I'm told that, okay, hey, this point is the ICR. Okay, I want to find the velocity of some point A here. Okay, so obtain velocity of A. How do I do this? First step is locate the ICR. This is given in this case. Okay, then I draw a straight line joining A and ICR. So join A and ICR. Okay, so I'm just going to join those two together. And then I have to make use of the right hand rule. Right hand rule. Okay, the velocity of A has to be drawn such that if I use the right hand rule, I get the same omega direction as the previous case. Okay, so velocity VA has to be drawn perpendicular to the line joining A and ICR such that upon using the right hand rule, I get the same sense as the given omega, right? I'm told that omega is counterclockwise. So what should be the direction of the velocity at A? It should be pointing this way. Okay, of course, this is going to be perpendicular to the line here. So this is going to be the direction of VA perpendicular to that line. Only then can I get the sense of the rotation to be counterclockwise. And then how to find the magnitude if I know the distance between the 2 points, right? So this distance is also going to be given to me, or A slash ICR. I can find out that VA is RA slash ICR multiplied by omega. Okay, this tells me the magnitude of VA. Okay, because I'm given omega, given the location of ICR, and then given the location of a point on this body. I know the distance, I know the angular velocity. Okay, so this is the last case that I wanted to discuss here. So very briefly, I want to recap. Okay, just the summary points that I had made. Summary and the usefulness of ICR. Instantaneous center of rotation. At that instant in time, it is a point on the body or outside the body about which the entire body is going to rotate. Velocity of the instantaneous center of rotation is 0 at that instant in time. This is extremely important. It is only at that instant in time. At the next time instant, I don't know what is going to happen to that ICR point. I don't care. Okay, and the ICR always lies along the line that is perpendicular to the velocity of any point in the body. I choose any point A or point O or point D. If I locate the ICR, I see that ICR is along the line that is perpendicular to the velocities of each of these points. Okay, it is not just one particular velocity, but any velocity on the body. The ICR has to be perpendicular to that particular velocity. Okay. And then the other thing is, if I know the velocity at a point and if I know the ICR location, then using the right hand rule, I can obtain the direction of the angular velocity, and I can obtain the magnitude of the angular velocity by saying that the velocity of the point is the distance times angular velocity. Okay, that's exactly what we have done here, magnitude and the direction. And for the direction, use the right hand rule. Align the fingers with the direction of the velocity. Your palm is facing the ICR, the palm of your right hand. You curl your fingers. The curl of your fingers is a sense. The direction of the thumb is the direction of the rotation. And in this case, it's pointing into the page, which is what we have drawn here in a clockwise sense. Okay. And so the idea is, if I can locate the ICR and if I know the velocity at any point in the body, I can find the angular velocity of the body. Okay. And the very last point, ICR is used only for velocity analysis. Do not use this for, please do not use the ICR for any acceleration analysis. Okay, this is something that you really have to keep in mind. Okay, this is used only for velocity analysis. All right, folks, thank you for your patience. I hope all of you are staying safe. Take care of yourselves. Bye-bye.